In this video, I want to do some more examples of interval and radius of convergence. So you'll see in this first example, we have an alternating series to begin with. So we're going to do -1 to the n, x to the n, 3 to the n, and okay. So let's set up our ratio test. So we've got -1 to the n plus 1, x to the n plus 1, 3 to the n plus 1, and then I'm going to do, it's n plus 1 plus 1. I'm just going to write n plus 2 right off the bat. We'll multiply by the reciprocal, because we should be dividing, of course, by the nth term. I'm going to multiply by the reciprocal. Yeah, and remember this is a limit as n goes to infinity, and it needs to be less than 1. All right, let's do some simplifying here. We're going to have a leftover x on the top. We're going to have a leftover 3 on the bottom. We're going to have a leftover -1 on the top. And everything that is a constant, so the -1 and 3, I'm going to bring out front. And then the x I'm going to bring out front because I'm kind of treating that as a constant because the limit is only as n goes to infinity. So with this kind of rewrite, I now have a -1x over 3 out front times the limit as n approaches infinity of n plus 1 over n plus 2, and I need this to be less than 1. So this limit right here, you can see we have the same power on top and bottom. So we use the coefficients as we go to infinity, and the limit, of course, is just 1. So we've got -x over 3 less than 1. And remember, we also have to put greater than -1 to incorporate the fact that it could have been an alternating series, and we need to recognize that we also might have some negative x values that will work. So I'd multiply everything by 3. And then I'd multiply everything by -1. And you remember what happens when you multiply by a negative or divide with inequalities is they change direction. Now, really, I still have that x is less than 3 and greater than -3. So, I mean, I could have almost just erased that -1 right here, just covered it up, and I would have exactly the same thing. So I'm going to go back because, of course, normally we see inequalities going the other way. So we should have -3x and 3. Okay, so right now I know the width of my interval is 6, so I know the radius of convergence is 3. But remember, to finish this, I need to check my endpoints. And just personal preference, I always like to start with the bigger one. Doesn't really matter what you start with, but so what I'm going to do is I'm going to plug 3 in for x. So right here. So that means I've got -1 to the n, 3 to the n, over 3 to the n, and n plus 1. And you'll notice that the 3 to the n's will divide out. So I'm left with -1 to the n over n plus 1. This is conditionally convergent. So I'm going to add an equal sign on the 3 because 3 gave me at least conditional convergence. And remember, all I'm doing is searching for what numbers I could put in that will give me convergence. So now let's put in -3. Okay, now I got to do a little algebra here. -1 to the n multiplied by -3 to the n on top, that is 3 to the n. So I got 3 to the n on top, and on the bottom I got 3 to the n and n plus 1. Well, the 3 to the n's divide out, so I'm left with 1 over n plus 1, and that by limit comparison to 1 over n, this will diverge. So this is my final interval because the negative 3 will not get an equal sign because that did not lead to convergence. So here's another example. I've got x to the n times n factorial. This one I think is a great little exercise in just logic, and maybe we could think about ahead of time. Multiplying by n factorial, we all know how powerful this function or this operator is. So think about what x might have to be that could possibly lead a multiplication of n factorial to converge. Okay, so let's do our n plus first term, so x to the n plus 1, n plus 1 factorial. And on the bottom, I'm just going to divide by x to the n and n factorial, taking the limit as n goes to infinity. So we do our simplifying. I've got a leftover x on the top. N plus 1 factorial divided by n factorial is just going to be n plus 1. So remember, I take the stuff that isn't with an n, I pull that out front like a constant. So I've got x multiplied by the limit as n approaches infinity of just n plus 1. This limit is infinity. So x multiplied by infinity is less than 1 or greater than negative 1. So now you need to ask yourself, what could I possibly multiply infinity by that would get me between negative 1 and 1? And the only thing you can do is 0. And maybe there's some logic here that you could say, well, we're always trying to divide, solve for x. Could you think about dividing by infinity? You know, kind of bad notation maybe, but maybe helpful to think about. And 1 over something going to infinity is 0. Okay. So the radius of convergence, well, this isn't even an interval. So the radius is also 0. Of course, there are no endpoints here. So the only x that will lead to convergence is if it's just a series of 0. In our last example for this video, we've got x minus 5 to the nth over n squared. So let's set up our ratio test. Multiply by the reciprocal. Taking the limit as n approaches infinity. I have one leftover x minus 5 on the top, so I will pull that out front. So I'll have x minus 5 multiplied by the limit as n approaches infinity, n squared over n plus 1 squared. This limit is 1. So I end up with x minus 5 multiplied by 1, which of course is just x minus 5. Between negative 1 and 1, I add 5. So right now I can tell you that the width of my interval is 2, so the radius of convergence is 1. And of course, to get the interval, we're going to check those endpoints real quick. So let's start with 6. If I plug 6 in up here for x, I've got 6 minus 5, so that's 1. 1 to the nth, that's just 1. 1 to the nth is always 1. So this series is just 1 over n squared. And of course, this is a convergent p-series. And the other, x equals 4, so I add an equal sign, to the 6. 4 minus 5, of course, is negative 1, so now I have an alternating series. And of course, this will converge absolutely. So I get an equal sign on that as well. And there is my interval of convergence.